In these videos, we are going to learn two definitions that are of huge importance to us as we begin our study of abstract algebra. In particular, we will learn about binary operations and we will learn the definition of a group. First, I'd really like to think about a binary operation informally. We're going to start with G being any old set in the world. Informally, all a binary operation is a mechanism for picking up any two elements of that set, combining them somehow, and getting back another element of that set. So if I were to pick up two different numbers and combine them somehow and get another number, that has hope of being a binary operation. On the other hand, if I were to pick up two elements, combine them, and get an elephant, I would be very surprised, and that would not have any hope of being a binary operation because I'm combining two like things and getting something very, very different. Now, when we talk about an operation being a binary operation, we're putting the emphasis of that property on the operation itself. That's when we call it a binary relation or binary operation. If we wish to change our vernacular a little bit and put the emphasis on the set as opposed to the operation, we will sometimes use a different word to mean the same thing, and we'll say that the set is closed under the operation. So saying that a particular relation is a binary operation on a set is the same as saying that that set is closed under the operation. Moving from an informal definition to a formal definition, formally, dot is said to be a binary operation on the set G if dot is a function that has domain, the Cartesian product of the set with itself, and range equal to the original set. Now I wanted to make a little aside that I'm using the words domain and range, which are familiar words to us, but abstract algebra and set theory occasionally use different words to talk about things. So before I move on, I'd like to define domain and range to make sure that we're on the same page. Domain is nicely what it has always been, no matter how you learned it. Domain is the set of inputs to a function. However, things get a little bit difficult to understand when you start talking about outputs of a function because there's two different sets actually going on here. There's the set of theoretical outcomes of a function and then the set of actual or realized outputs of a function. And those two sets need not be the same. And so typically the word that we use for the set of theoretical outputs would be codomain, and the set of actual outputs would be called the range. That's a set theoretic way to think about it. However, when we move into abstract algebra, it's more common to see the set of theoretical outputs be denoted by the range, and the set of actual outputs be called the image of the function, and I tend to use that vernacular throughout abstract algebra. Whereas range in set theory often means the set of actual outcomes of a function, I'm going to call that the image. And the set of theoretical outputs of a function, I'm going to call the range. So we need to be clear on that just so that we understand this definition of a binary operation. I'd like to do some examples and non-examples of binary operations to drive home a couple of points. I have 4 examples on the screen. Although we're just learning about this definition and the formal definition is a little bit daunting, just keep the informal definition in your mind. A binary operation is one which can pick up any two elements of a set, combine them, and give you another element of that set. Just keep that definition of a binary operation in mind and look at these 4 examples, and in your head, answer yes or no. Do I think this is a binary operation or not? Pause and think about each one for a minute, formulate your answers, and when you're done, unpause. As we go down the list, our answers for these 4 should be yes, no, no, and yes. Let's walk through them one by one. The integers under subtraction. If I pick up any 2 integers in the world and I subtract one of them from the other, first of all, that's always possible, and the output is always an integer. I never subtract one integer from another and all of a sudden get like a fraction. And so this is a good old example of a binary operation. The integers under division, however, do not work. Although I could pick up 4 and 2 and do a division, 4 divided by 2 is 2. Both of those things are integers and everything works great. All I need is one counterexample in order for this to fall apart. Because I can pick up 4 and 3 and do that division, and what I'm left with is no longer an integer, this is not an example of a binary operation. The answer for number 3 is also no. The example we're looking at is picking up 2 natural numbers, and then instead of looking at just their difference, that could be complicated, and if I picked one number to be a that was smaller than b, then a minus b would be a negative number and it would no longer be a natural number. That would be problematic. So my attempt to fix that is to put absolute value signs around that difference so that in the case that a is smaller than b and I end up getting a negative number with this subtraction, by throwing absolute value signs around that difference, I'll pop myself right back into the natural numbers. So 3 seems at first glance like it's going to work as a binary operation. However, because we don't think of 0 as a natural number in mathematics, in computer science we do, but in mathematics we don't, if I pick up 2 numbers that happen to be the same, which is a possibility I need to think about, if a and b have the same value, their difference will be 0, the absolute value of 0 is 0, and 0 is not a natural number. So it truly is enough for there to be one problem to totally discredit something from being a binary operation. Last but not least, I want to show you that things that don't sound mathematical at all can in fact be binary operations. If you imagine having as a set the set of all colors, and our method for combining 2 colors is to pick them up and just mix them together like the color kittens are doing over here, book from my youth, that will give you another color. And because we're looking at the set of all colors, we'll have that color in our collection. And so this would be a perfectly valid way of picking up 2 things, combining them, and getting a thing that was in the set that I considered. So perfectly non-mathematical things can be binary operations, while things that are very mathematical in nature can fail to be binary operations. And it's important to make that distinction before we move on.